Hey everyone, and welcome to The Explainer. If you've ever sat in a math class just staring blankly at a grid of X and Y axes and wondering, when on earth am I ever going to actually use this in the real world? Well, you're definitely in the right place today. We're going to completely shatter the idea that school math is just, a bunch of theoretical textbook exercises. Get ready, because we're about to reveal the invisible mathematical architecture that literally builds and guides our entire modern reality.
To kick things off, I want you to really think about this seemingly impossible question. What in the world could a treacherous, high-altitude mountain highway in the Himalayas possibly have in common with that smartphone sitting right there in your pocket? Specifically, what happens when it pings a satellite way up in space?
Okay, let's dive into this. The answer? It's coordinate geometry. Honestly, those abstract formulas you learned back in school, the distance formula, finding slopes, mapping coordinates, they aren't just random numbers on a page. They're the actual literal blueprints and the silent engine that runs the physical world. Let's look at exactly how these formulas build our reality, and we'll start right from the ground up.
Section 1. The Himalayan Highway Crisis. Alignment Problems.
So, if we look at India's national highways, specifically the incredibly treacherous Sojila Pass under the Bharatmala Pariyojana, we can see a massive historical crisis. For a long time, mountain roads were built using something called empirical contour following. Basically, engineers would just look at the mountain and map out a path of least resistance, literally just following the ground's natural, uneven shape. And this created what's known as a snake effect. We're talking about winding, twisting trails with hundreds of dangerous hairpin bands. It was hugely inefficient, adding up to 25% to the total travel distance and bumping up fuel consumption by 30%. What modern engineering really demanded was a total shift to a precision-engineered geometric design, something built on a stable geometric locus.
And here's why that shift was literally a matter of life and death. When researchers analyzed the traffic data, they found these terrifying locations they called kinetic black spots. Vehicles were crashing, but get this, it wasn't because of speeding. They crashed due to coordinate drift, because the roads were just blindly following the dirt, the slope, the m in your old algebra equations, changed continuously and instantly right in the middle of unbanked curves. They completely lacked a mathematical transition spiral, which is absolutely crucial to smoothly guide a heavy, fast-moving mass from a straight line into a curve. But the danger wasn't just the sharp curves. There was also a massive issue with structural locus failure. By using LiDAR technology to create 3D maps, geologists discovered that these old contour roads were actually built directly on highly unstable rock debris known as talus slopes. By trying to build on a simple contour locus rather than calculating a strict mathematical one, the roads were fundamentally flawed. They were essentially doomed to just slide right off the mountain.
Section 2. The Math of Infrastructure. 3D Spatial Mathematics.
To fix this chaotic situation, there was a massive, sweeping shift. The government made a national commitment to replace all that guesswork with 3D spatial mathematics. They decided to stop just, following the ground and start literally cutting through space using highly precise X, Y, and Z coordinates to build these massive modern viaducts. So, how exactly do you translate a giant, rugged mountain into math? Well, it happens in 4 major steps. First, planes fly over the terrain firing lasers, that's LiDAR, to map out every single square inch into a massive point cloud of coordinates. Then they use area formulas for legal land acquisition, section formulas for structural alignment, and finally, those transition spirals to ensure the actual physics of driving the road are perfectly safe.
Now, what's really fascinating here is how pure math solves uniquely human problems. Phase 1 of building any highway is obviously buying the land. But instead of arguing over vague physical landmarks like, say, an old tree or a big rock, every single plot is assigned exact boundary coordinates. Engineers use the shoelace formula, which calculates the area of a polygon based entirely on its vertex coordinates, to figure out the exact square footage. The computer does the math, the bank pays out the exact compensation, and decades of bitter legal disputes just vanish, all thanks to a formula.
Then we get to the actual skeleton of the highway. Imagine having to place 10 massive pillars across a deep, jagged ravine. The base of the ravine is completely uneven, rugged terrain, but the road sitting on top has to be perfectly flat. So engineers use the section formula, finding an internal point using an m to n ratio to determine the exact x, y, and z coordinates for the base of every single pillar. That basic textbook formula you learned is quite literally holding up millions of tons of solid concrete.
And the scale of this mathematical application is just breathtaking. The Bharatmala project alone represents an investment of over 5 trillion rupees.
By applying coordinate geometry to road alignment, travel times on major routes like the Delhi-Mumbai Expressway literally dropped in half, going from 24 hours down to just 12 hours. And by replacing those sharp, guessed angles with mathematically calculated transition spirals, those deadly, accident-prone black spots, they've been reduced by 60%. So, to summarize our earthbound application here, the core tools building these highways aren't actually the massive construction vehicles. They're linear and quadratic equations. The main variable is the exact x, y, z center of the road, and the major transition point was mapping the physical Earth into a digital point cloud. Every single time you drive on a perfectly smooth highway, you aren't just rolling on asphalt. You're driving on a mathematically optimized locus.
Section 3. The Navigation Crisis. Lost at Sea.
Okay, let's scale things up. We're moving from the mountains of Earth to satellites 20,000 kilometers in space to see how geometry solved the global lost-at-sea navigation crisis. See, for most of human history, navigation relied on something called dead reckoning. This meant using angles from stars, the winds, and compasses to guess your location, which is fine until it gets cloudy, and then you're in real trouble. The modern solution was completely shifting how we view the planet itself. We moved to a 3D Cartesian framework. In this incredible system, the exact center of the Earth is defined as the ultimate origin point, 0, 0, 0. And every single thing on the entire surface of the planet is mapped relative to that deep inner core. But the villain of this era was once again coordinate drift. Imagine an airplane flying over the middle of the ocean relying purely on dead reckoning. Just a slight crosswind meant the coordinates the pilot had on their map became increasingly, progressively wrong. This created a terrifying uncertainty circle that grew larger every single hour. After a 5-hour flight, a plane could easily be 50 kilometers completely off course, which historically led to some incredibly tragic maritime and aviation disasters.
Section 4. Space and Time. The Navstar Project.
To finally fix this deadly drift, the U.S. developed the Navstar project. And the real breakthrough? It actually came from tracking the Soviet launch of Sputnik using the Doppler effect of its radio frequency. Scientists realized something brilliant. If we can know a satellite's exact coordinates in space, we can work backward to calculate our exact location down on the ground. They achieved this through a process called trilateration. Here's how it works. If you know your exact distance from one satellite, your location is somewhere on the surface of a giant 3D sphere. Add a second satellite, and those two spheres intersect to form a giant circle. Add a third satellite sphere, and that circle gets narrowed down to exactly 2 points, one floating out in deep space and one right exactly where you're standing on Earth.
So the absolutely crucial point here is how we actually figure out that precise distance to draw those giant spheres in the first place. Well, we use the 3D distance formula. But there's a catch. It only works if we solve for a fourth unknown variable, time. Distance equals the speed of light multiplied by the time it takes the satellite signal to actually reach you. Guys, we are literally doing math with the speed of light here. How cool is that?
But here is the terrifying geometric conflict we run into. The satellite up in space is using a multi-million-dollar, incredibly precise atomic clock. But your smartphone, it uses a cheap, basic quartz clock. Now you might be wondering, does a tiny fraction of a second really matter? Well, because light moves so unbelievably fast, if your phone's clock is off by just 1/1000th of a second, your location on Earth will be wrong by 300 kilometers, literally. So mathematicians had to treat time as a strict fourth coordinate to perfectly synchronize your cheap phone with the satellite's atomic clock.
And when you get that math right, the real-world impact is just astronomical. GPS technology contributes over $1 trillion to the global blue economy every single year. I mean, it enables precision farming in India, where giant tractors are guided to within 2 centimeters of accuracy. It allows for advanced regional networks like India's NAVIC system, ensuring national security and completely independent logistics. So wrapping up this GPS case study, the fundamental tool at play here isn't magic. It's literally just the 3D distance formula and the equation of a sphere. By moving from simple 2D flat planes to complex 3D spatial geometry, we've managed to solve global logistics, enable those food delivery apps we all use, and completely revolutionize disaster management. That exact math is continuously running on the little microchip inside your pocket right now.
Section 5. The Architecture of Reality. The Geometric Grid.
We've gone from the massive scale of satellites flying 20,000 kilometers up in space, all the way down to mountain highways carved through the rugged Himalayas, right down to the little food delivery app pinging on your screen. And it is all built on the exact same math. I really want to leave you with this final, empowering thought.
When you study this, you aren't just learning how to find the distance between two random points on a page. You are learning the math that connects vast cities and tracks satellites across the stars. You are an active participant in the most sophisticated geometric grid ever built by humanity. So the next time you look at a simple XY axis, maybe ask yourself, what invisible architecture will you build with it next? Thanks for joining me on this explainer, and as always, stay curious.